So the topic that we're going to learn today is T confidence intervals. Plus what we are going to do is we're going to discuss the project. All right. So coming to T confidence intervals, uh, what is the need for T confidence intervals and what are they basically, right? We see that data is naturally distributed normally as long as the sample population size is large and the sample taken out of the population size is also large. You agree with me on this? We have seen that it's a natural distribution, not something which is mathematical only. We showed that um, uh, with that apparatus that was there in one of those slides in the previous class, right? We say okay, the sand will fall either on this side or that side and so on, and ultimately we will get uh, a normal distribution, right? So what is happening is that in reality, it so happens that when the sample size is small, all right, the let's say if the normal distribution is this way, okay, if the sample size is small, this distribution will be such that it will have fatter tails. What does that mean? Means the data where it was not even expected would be more in this region, which is far away from the mean center, all right, and less in this region. So now this fatter tails will change your quantile value, right? Normally what we see is we say we have an equation which is something like this. We have the estimator and plus or minus the quantile value and the standard error of the mean, right? So this is how the formula goes for us to compare the confidence intervals. This is what we did the last time. Are you clear about this much from previous class? Correct? So so now this is an observed phenomena that the tails are fatter. Okay, so Kameshwar is clear. What about the rest of you? Just see if there's any shortcut for raise hands, and it's easier to just do raise hands. So I get an idea. Uh, uh, if it is easier for you to raise hands rather than type, then just show that to me, and I know that you understood it. Okay. So what we are saying is that because they are fatter tails, there is a actually when say I'm interested in 95% quantile, right? So if the tail was not fat, let's look at the black one, right? If the tail was normal distributed, so my 90, let's say assuming my 95% hits here, right? Which means the area under the curve, that is a black curve from point A to point B, is 95% of the total area, all right? Okay, but because the tails are fatter, now for the area to become 95%, it is between point, let's say, C and point D. Okay, so now what has happened? This length, which earlier was only this much, all right, now has become this much, and on both ends, right? So if I was calling the length which is A or B equal to ZQ, I would call the length C or D equal to TQ. Is this fine? Now, in the normal distributed curve, what we have done is when we created this equation, we were typically using the standard normal distribution, all right, to come to this, but that's not necessary. But anyways, so ZQ has been now replaced by TQ. So we say that when the sample size is small, okay, we use the T distribution and T confidence intervals. So the distribution is T distribution, which is represented by TQ, and the confidence interval becomes this estimator plus minus T quantile into the standard error of the mean of the estimator. Okay, and now he says that if you were to decide on a rule whether to choose T interval or normal interval, he says always use the T intervals. Why so? Because the T intervals tend to become close to normal interval when the sample size increases. So it serves both purposes. When the sample size is small, it behaves different from normal distribution, and as the sample size increases, it anyways becomes same as the normal distribution. Okay, so let me show you sum of the, so I'm just showing you the graph, all right, the data, right? So this is the t distribution data for different confidence levels, okay? And so different confidence levels. Now there is this concept called degrees of freedom in t interval. What does the degrees of freedom mean? It is conveying the sample size. So if the, say, let's say our sample has sample size is 10, then the degrees of freedom will be always one less than the sample size, okay? Because 1 degree of freedom is lost in calculating the sample mean, okay? So now if you look at the sample size 10, right, and you look at the confidence interval, that is 95, that is this, okay? Here what you see is at sample size 10, the confidence interval sample size 10, which means degrees of freedom will be 9, right? And confidence interval of 95% is a value which is 2.262, and this value keeps on reducing, okay? And at 100 it becomes 1.98, and as it tends towards infinity it becomes 1.96, which is the same as the value for normal distribution, right? So there's a t distribution table which is available, which, I mean, before people had softwares like R, they still used to work on statistics, okay? And they had these tables, and they used to plug in the values from these tables, okay? All right, so we're saying this is what it is about the t distribution. So now who invented it? There was this guy called William Gossett, and why did he use the pseudonym? Because he was working for a company, and the company said, look, you want to publish this research, you can't publish it with your name, you can just publish it anonymously, right? So it has thicker tails. Now it has only one parameter, which is the degrees of freedom. So a normal distribution has two parameters, which is mean and standard deviation. Here the only parameter that is available is the degrees of freedom, okay? And it assumes the underlying Gaussian IID form, that is x bar, right, minus mu. Now mu is the population mean here, all right? So x bar is the, this, what is the x bar? Sample mean, right? And now here, instead of sigma, which would have been the population mean and is used in normal distribution case, right, we use S, which is the sample mean, and N is the sample size. So the only thing that has changed is this S, okay? Everything is the same, all right? This is population mean, sorry, this is population standard deviation, this is population mean. So I'm using this. So with n minus 1 degrees of freedom, all right? I am not audible. Others, I'm not audible to anyone. Okay, Sarvani, it's audible. Okay, Kameshwar, looks like some problem with the, how about the others, boys hostel? I will explain. So this is a concept which we have already done, okay? But only thing that we are saying is that in the case of even Raghav is not able to hear. Looks like boys hostel, the signal is not good. Okay, so we're saying this is one thing which is different here. We have S, okay, instead of sigma. So the sigma is replaced by S. The sigma is the population standard deviation, whereas this is sample standard deviation. Okay, that is all. Okay, so this is what we have changed in the t distribution, okay, when we look at the formula. Now this will follow we're saying that this will follow the Gaussian T distribution with n minus 1 degrees of freedom. We will look at this and it will become more and more clear. So if we were to replace S by sigma, the static would be exactly standard normal now, all right? And so intervals in this case for us are this, right? We say x bar plus minus t n minus 1 because n minus 1 degrees of freedom, okay? S upon n square root of n, all right? So this is what we get for the T distribution. Okay, so now for this, what we will now go ahead with doing is we will get into R and the so is this readable? So I'm going to select lesson 9 in swirl. You know, swirl is amazing. So he's asking us some questions. Okay, so what's the first question he's asking? He's saying that in the asymptotics lesson, where what is the asymptotics lesson? We say that the sample size is large, right? So we're using CLT and the normal distributions. Now he's saying here Q norm is represented by what? So Q norm represents what? It represents a Q norm function represents what? It represents a specified quantile from a normal distribution, right? So in the asymptotics lessons, we also saw that Z static is this. Z is equal to x bar minus mu upon sigma square root of n, which follows a standard normal distribution. This normalized static is especially nice because we know the mean and variance. So mean and variance in the case of Z statistic are what? 0 and 1, right? Because it is standard normalized. So the mean and variance of the standard normalized are fixed and known. Now we will define the T static, which looks a lot like the Z. So this is what it is, right? The only difference between the two is that the population standard deviation sigma in Z is replaced by the sample standard deviation in time t. So the distribution of the T static is independent of the population mean and variance, he's saying. Instead, it depends on the sample size n. So I don't know why he's saying that the distribution is independent of population mean, because mu is still there, all right? Variance, of course, is not there. Population variance is not coming into picture, and definitely T distribution is independent of that, okay? But I guess it still depends on mu, right? So I still have to verify this, but I think it is only that it doesn't depend on the variance, okay? So as a result, for T distribution, the formula is changed, right? And we have a different standard error. So we'll use the sample standard deviation when we estimate the standard error of the estimate instead of using the so in this expression, what expression represents the sample standard deviation S, right? Oh, sorry, fourth option. Okay. The T confidence intervals are very handy, and if you have a choice between these and the normal, we've already discussed this. We should always use the T normal distributions rather than the T distribution rather than the normal distribution. Okay. So the key thing is that they have a thicker tail, right, than the normal distribution, and then the degrees of freedom is n minus 1. So and as the degrees of freedom increase, the T distribution gets more like same as standard normal, and it is centered around 0. So we already know this. So if we replace the sigma by the static T, it would so basically it is the same as standard normal if S is replaced by sigma, right? Sorry, okay. So what he has done is he's taken code from the slides and a function called myplot, which makes the integer df, takes it as its input and plots weight. So basically we had dnorm, right? We said we had dnorm. So I say dnorm of 0.975. All right, I give the population. Where the population is 0.975, I would get the answer as 1.96, right? hold on, sorry, not d norm, I have to say the q norm, right? So I get the answer as 1.96, right? So similarly we have something called qt. So qt will have the parameters which are degrees of freedom and uh, the population. So I said p is equal to 0.975 and then the degrees of freedom, let's say I say 10. So I get 2.22. This is what we saw earlier. If I keep on increasing the degrees of freedom, let's say I make it really large, my answer is close to what I get from Q norm. But if I make it really small, let's make it 4. Suddenly I have a much larger answer, which is 2.77. Is this clear how the quantiles are changing? So instead of Q norm, R norm, now we have R, T, Q, T, etc. Let's just look at the help. I say QT. Okay. Uh, So we have all these functions, right? So similar, just that norm has been represented by T now. Okay. So coming back to the swirl assignment. Uh, so or let's try it out here. Let's try to plot these curves. Okay. In our console itself, we'll do it. Okay. Uh, okay. So we have a swirl going on here. So he has given us this plot called my plot. Okay. So my plot will take an input which is the degrees of freedom. So I say my plot 2. So what do we get here? Just look at this. So now normal distribution gives a curve which is like the red curve, all right? And the t distribution will give us a curve which is the green curve. So we see that they have fatter tails here. Okay. So now if we are changing this number, let's say we make it 20. I say my plot 20. Now if you notice that both of them are almost same. So is this concept clear that how are t distribution behaving? Okay. So now what he's done is he's comparing the two. He says he's created another plot. He says my plot 2. Okay. With now I'll explain what is done here. If you so basically we're saying quantile, right? In the case of uh, uh, this is the case with 2 degrees of freedom, right? With 2 degrees of freedom, let's see what the number looks like. I say qt with 2 degrees of freedom. I get 4.302, right? So for standard normal, it is 1.96. So this plot, we're not going through the code of this for now. This is what we want to focus on is just to understand the things conceptually. So here I'm plotting the normal distribution quantile, and here I'm plotting the t distribution quantile. So I'm comparing one with the other, right? From a value for a value which is greater than 0. So basically this is 50 percentile point, right? 0 is 50 percentile. We know this, right? Half of the values lie below 0. Okay, and then it increases. So the green black line is 1.96, right? So 1.96 on the normal distribution is equivalent to 4.3 on the t distribution. So this is what this graph depicts, that how the values change, how it starts deviating. Okay, the t distribution. All right. So you're saying what's the value? Okay. So same thing I'm running now with 20 values. Okay. So suddenly now my graph, if you notice the two lines are very close to each other. All right. So this is how it goes. Okay. So coming back to our notes. So this is what he's done here. This is done with the code. Okay. So what are the key observations? First is that the data is still IID normal. Okay. So so this is the assumption. The t interval also assumes that the data is normal. Okay. But it works well whenever the distribution of data is roughly symmetric and mount shaped. So it's not necessary that it has to be IID normal. All it needs to be is symmetric and mount shaped. Okay. In fact, the whole concept is that we are saying the data is actually not normal, right? So paired observations are often analyzed using the t intervals by taking differences. We will understand what a paired distribution is. This is a question here. Okay. For large degrees of freedom, t quantiles become the same as standard normal quantiles. Perfect, right? So for skewed distribution, he says the spirit of t interval assumptions are violated. So they don't hold good. Okay. So we will not bother about this in this class. For highly discrete data like binary, other intervals are available. This is not working. So t intervals will not work. Okay. So now what we're going to do is, wait, let me see if we need to go through this, or shall I take you through the project for now. Okay. All right. So this much was for the t interval. We are going to come back to this. Okay. I will briefly touch upon the project. Okay. Once we have taken care of that, we will come back to this part of the thing, because project has two parts. Project one is from the previous week, and project two, or the second part, is from this lesson. And since we have presumably only the last class today, therefore I'm going to first discuss the project as well, because the submission is for Sunday night. Okay. Do you want to do that, or if you are okay, I can give you another class, but when would that be actually? It can only happen maybe Sunday night, because I have a course going on and tomorrow is the full day. Uh, how do you want to do it, so that I can give you more time for this week's work? Or shall we just discuss the project now, and that will take care of ensuring that the deadline is not missed? Which way do you want me to proceed? Is another class possible? But that's only Sunday evening. I think we'll focus right now on just trying to wind up everything today, so that you don't need a class on Sunday evening. Are you able to hear me? Okay. Perfect. So we will start discussing with the project. Uh, Okay, so what is this project about? So there are two parts to the project. First is a simulation exercise, okay, and the second is basically inferencing you have to infer certain things using the t test distributions. All right, so t distribution is what you will use. Okay, so now here what he's saying is that you need to create PDF. This is important. All right, and he says you can use whatever software that you want to use to create the PDF to submit finally, and you will use knitter. Now for those of you who had not attended the previous class, that is the reproducible research, today's class might come in handy, because whatever new was learnt in that class will get discussed today. All right, so it will get covered up. I will kind of brush through it quickly, so that will get taken care. So now let's first look at the question. What is the question here? So first question says so there's something called exponential distribution, right? It is represented by REXP. Okay, let me show that to you. If I say REXP, okay, let's say 1000 values. Okay, I'm plotting 1000 values, and what is there is something called lambda in this. All right, so let me use the lambda as 0.2, and then plot a histogram of this. Okay. So what I get is this. So basically it's exponentially decaying data effectively, right? That's what the data looks like. So if I was to have larger data, all right, and then I say bin or breaks is equal to 50, I'd get a more neater curve. Sorry. Yeah, you can see this. So how the data is decaying. All right. So now what I'm going to do is, so he says that we have this exponential distribution, which we'll simulate with R, where lambda is the rate of the parameter. Okay. And the mean of exponential distribution is given by 1 by lambda. And at the same time, standard deviation is also given by 1 by lambda. So this is the property of the exponential distribution. Okay. So for our purpose, we're saying the lambda is equal to 0.2. So in this simulation, what you are going to do is you will investigate distribution of averages of 40 exponentials. All right. And now note that you will need to do 1,000 or so simulated averages of exponentials. So what are we required to do here? Let me show it to you. So we're supposed to have we want to take the averages of the 40 distributions of 40 values, which means what? Let me look at I say Rx, all right. So 40 comma 0.2, all right. So this is what I have. Okay, so this is my sample. Let me call it S data. All right. So this is my sample data. Now what I'm interested in, he's saying take the mean of this. All right. So I say sample data mean, okay, is the mean of these values. Is this fine? So now what he's saying is repeat this thing 1,000 times at least. And then he wants to know about the population, this data that we get. Okay. So now how do I repeat this 1,000 times? One is the for loop, but maybe the easier way would be, let me say I generate this, if I was to run this experiment 1,000 times, which means how many times am I generating the random variable? 40 into 1,000 times. Is this clear? Right? And then I can kind of, split it up and create the data. So what I will do is I say, let's say my n is 40, okay, and let me call it m. M is this number of times I'm taking the samples, right? So I say 1,000, and so now what I'll do is I say my sample data. I say sample data all. Is REXP. How many times? I say n into m data points with a lambda of 0.2. All right. So I've created my data. Now I will convert it into a matrix. I say my sdat matrix form is equal to matrix of which data? Stat underscore all. And how many rows am I interested in now? 1,000, which means I say m number of rows and n number of columns. So this will convert my same data into the format of the matrix. And now if I want to apply the apply function directly, right, on the margins, which means each row wise I want to sum up the data. What I say is I say my S data mean, right, sample data mean. What would that array be? It would be apply on which data? Stat underscore matrix on each row. And what do I want to do? I want to take the average of this. All right. So what I get is okay, Sirish. All right. So I say S data is equal to, so I'm running the function apply on this. So I get the S data means. Now let us look at this S data mean, right? What we'll do is I'll just draw a quick histogram on this. Okay. So I say histogram on S data underscore means. All right. And let's see what kind of a graph we get. If you notice, the data which was exponentially decaying, when I take the mean of that data and repeat that many times, tends to be looking like normally distributed. Got it? Have you understood what we did here? Okay, Sarvani got it. What about the rest of you? Okay. Yeah, Sarvani, you got it, I know. What about the remaining people? So, what about the rest of you? Debashri, Nandana, have you understood what we did here? Or do you want me to somewhat? So basically, what we did is something like this. Let me go to the end of my slides. Okay. What we said is, so we created this sample data, right? So we had sample data of data which was something like this, right? So we took 40 random values. So our data, so 40 random values of this, right? So when we take 40 random values with a specific lambda, every time our lambda is going to be 0.4, right? So 40 random values we take and we take the average of that, all right? And then we repeat this 1000 times, all right? Then I have these 1000 averages. If I was to plot these 1000 averages, my data would be bell shaped. Is this clear? This is what we have done, and I've used formula for that. What I did is I created actually, uh, so I, because I'm creating randomly the data, so I can create 40 into 1000 times the data. Then I put it into a matrix, right? I say 1000 here, 40 here, all right? And then I apply, so I then do the apply function, and what the apply function does is it works on each of the rows. So it will pick up this row and it'll sum of all these values. Okay, so 40 values are summed up. Rather, I'll take the average of these 40 values. What I get is effectively the same experiment repeated 1000 times. So I straight away get 1000 values. Okay, if these 1000 values were to be put in the function called histogram, right, we'll see that the shape comes up something like this. Is it clear, all of you guys? Raghav, Abhishek, now it's clear. Okay, all right. So we've done that. Let's come back to what else is he asking in the questions. Okay. So we're saying, so you need to do 1000 or so simulated averages of 40 exponential means. That's what we did. Okay. So illustrate via simulation and associated explanatory text the properties of the distribution of the mean of 40 exponentials. Okay. So what all are we required to do? To three parts to it. So first is show where the distribution is centered at and compare it to the theoretical center of the distribution. When you say centering of the distribution, what do you need to do? You take the average, right? So if I was to take the average of the standard data mean, I say mean of, oops. So if I say mean of my S data underscore means, all right? What do I get? So I get a value which is around 5. Okay. Now theoretical mean should be what? 1 upon lambda, right? So what should be that? That should be 1 upon 0.2, which is 5. So we see that what we created and what is there, what should be there as the theoretical mean are close to each other. Have you got this? I will walk you through my code as well. Okay. All right. So by the way, there's an easier way to plot, right? I was doing histogram, right? If I was to just do density, if I say plot, okay, and then I say plot what? The density of S data underscore means. All right. Let's look at this plot. So this plot is more easily understandable rather than the histogram, right? So this is what the plot looks like. So how do you do it? Use the function density and then straight away use the function plot. You don't need to use the function histogram. This is fine. So we've kind of done the part one of the question, right? Second part he's saying is show how variable it is and compare it to the theoretical variance. Now first let us look at what the theoretical variance should be. We've seen that on the top he's saying that standard deviation is also 1 by lambda, which means the variance will be 1 by lambda square, which is nothing but 1 divided by, so 1 divided by 0.2 into 0.2, right? So my theoretical variance should be 25. Okay, let us see what my data gives. If I say variance of S data underscore means. Wait, have I made a mistake somewhere? No. So the theoretical that show how variable it is and compare it to the theoretical variance of the distribution. Uh, no, we're taking the averages, right? So now the distribution has become what? The distribution is no more R exponential. The distribution has become normal distributed, right? So the normal distributed will be having a what's the formula for the normal distribution? It will be uh, s square by n, right? Uh, for normal distribution, it is a normal distribution generally will be having sigma square, but because it is the uh, sample size, for the sample size it becomes sigma square by n, right? So if you were to look that, so so first we look at the population, right? So that will be sigma square divided by n, right? So now sigma is given as 1 by 1 upon lambda, right? So theoretically we'll get the value as, so this and this whole thing divided by 40 divided by 40. What do we get? 0.625, right? So we're getting a theoretical mean which is 0.625. Sorry, theoretical standard variance, theoretical variance is 0.625, and our variance is coming out to be 0.60 or 0.61. So pretty close, right? If you were to increase the data size, you will see that the answer is more closer. I mean, I can quickly show that to you. What I will do is, let's come back to where we created it, right? I'm increasing, wait. So what am I increasing? I'm increasing the number of times that I've taken the sample. So I'm taking the sample 1 lakh times now. Okay. So I'm repeating this experiment. So I get my stat all. Okay. And from that, I create the matrix. So I create a matrix. All right. And from that, I do the apply function. Okay. just type it out. I say apply. Oh, wait. Okay, as data, so I'm applying it. Okay, so now it will take some time, because what are you doing? We have 1 lakh data points. Okay, right? So now if I was to say the variance of S data means, we have the new S data means, right? So if I say the variance, do you notice what the answer is much closer to 0.625 now? I'm getting 0.628. Got it? So as I increased, I did not increase the sample size, by the way. All I did is I'm taking multiple, samples. So I've just increased the number of times I'm taking the sample by 100 times. And so asymptotically, we can say that the data is tending towards the theoretical mean. But in our case, we'll stick to 1000, right? And when we stick to 1000, we will say, okay, our answer is this much. And that's how it is different from the theoretical answer. Okay. So we've done this. And then he says that the show that the distribution is approximately normal. So how do we show that, right? So basically we just plot it, and we also plot the normal curve, and we compare the two. All right. So he's not asking us to perform a test whether it is normal or not. If you were to perform a test, you will see that it is not normal. But all he wants us to do is show that it is approximately normal. So the key word there is approximately normal. Okay. So and there's another test called QQ test, right? So QQ test does what? If you remember, we saw two graphs today, right? First graph was where the distribution was compared, the t distribution versus normal distribution, and the second graph was where we had the two lines, right? And those two slanting lines, the upper one was curving up, right? So that is basically the QQ plot. So we will look at basically quintile to quintile plot. So we will look at a QQ plot as well as a normal distribution versus t distribution graphs to answer this question. What I'm going to do is I'm actually going to make you code walk through my answers right here. So now how many of you have no idea about how RMD file is written? So I will kind of explain that to you. Any of you have no idea what an RMD file is and what it does? All of you have an idea how it is? What is an RMD file? Hello? Who all understand what is an RMD file? And who all do not understand? Can you guys hear me? Am I audible enough? Hello? Can you guys hear me? Raghav, you can hear me? All right. Oh, I see a lot of people showing offline. Is it because the net has gone bad? I see Debashri shown offline, Nandana offline. Or they just switched on but not on the machine. Is that how it is? Attentive, I see everyone is attentive. The software tells us whether people are, on the machine or not. So you guys can hear me. But I see a lot of people offline. What is wrong? Yeah, but is the signal gone bad or something? Like see I see Sarvani two IDs. One is offline, the other is there. Okay, let me anyways proceed. Yeah, basically same as reproducible research, right? So let me just walk you through the code. If I was to create a new file, right, it will always anyways have this title and all. Okay, what I'm doing is I'm just knitting my file to show you the output, and then we'll see how the output got created. Okay, so this is what my output looks like. So I'm specifying an objective, all right, and so you don't need to kind of verbatim use this. I can give you many examples of other people who have done it. Maybe read through all of that and then create your own. Okay, so then I have some code and then I'm showing the graphs. Okay, so this is the comparison, first comparison, all right. This is the second comparison, and then I'm adding something in the appendix. Okay, so now how did we create this? What is it that you notice which you want you to understand? How did you get that? For example, how did you get this red thing, right? How did you get the objective as bold? Okay, and then how did you get, if you notice this, here I say calculate center of mean is this, is equal to this, is equal to an answer, is a number here, right? So similarly, I say theoretical is a formula, then some calculation and an actual, right? And I'm using formula here. I'm not just typing it. So here the answers have formula as well. Okay, so let me show you that part. Okay, so anything that I want to do in bold, okay, wait, let me shrink this size. So anything I want to do in bold is in the two stars here. So objective has become bold, if you notice, right? And then anything I want to show it in red, for example, like this in a box in red, I do this. I use backtick, single backtick. All right, so single backtick, and I'll show you that. Okay, then moving further, say I want, so here I wanted to do combination of both. I wanted to show question one both as bold as well as in that box. So I've done this. I say double backtick, single backtick, and then the double stars. Okay, now let us look at how did I do this part. So here I'm just putting the code. Okay, and so I'm generating everything just like we did it in class, and then I'm putting the plot in the appendix. Why am I doing that? Because there is a limitation. They say 3 pages of your file and then 3 pages of appendix maximum, right? So I just wanted to ensure that I'm not taking away, I'm not overshooting the required limit. So now calculate center of the mean of the distribution. So look at the code behind that. So here I'm saying I want to put this into red. So I put this into red by having written this. Similarly this. Now interestingly, now this is what I want, right? 5. I want the answer as 5 and I've calculated it. So it's a calculation here which is data M. Okay, where is my data M? It is this. Now data M that I want to show is a sprintf, which is basically mean of exponential data, the average of that. Okay, so what we had, and then I want to show it in up to 2 decimal places. So there's a function called sprintf, which is an R function. So I use that to get the value of data M. Now next thing that I do is in reproducible research, if I use backtick and then I say R and then I say an expression, it will compute that expression. All right, so instead of data M, it will replace it by the value of data M. Similarly, this part I say 1 by lambda, okay, and which is nothing but 1 by 0.2. This is what I want to write as it is, and then I say R 1 upon 0.2. Notice one thing here. In R, see, I can just say 1 divided by 0.2. So this divided by is not this side. All right, it is this side. Is this clear? Normally what you will, I mean, when you want to represent, you will just use a backslash, but it's a slash. So that's the difference. Is this clear? So you should be clear about which is the divided by sign. Okay. Now what I do is I actually compare the percentages. I said how different is the answer. So I said theoretical center minus this. So I get the difference is about 0.0033, which is about 0.07%. So I've computed these values here. Okay. And then I just plug them into the. So is this part clear? How you can create your file? I mean, the only new thing that is there is backtick R and then the expression. If in case you had not used it earlier, I had not used it. For me, this was new at least. Okay. So similarly, you do the second part of the project. Okay. And then third part, we'll look at the code of that. Okay. So what I'm doing is I plot the exponential data, okay, and then I draw a line uh, at a vertical line at the mean of the data. Okay, so let's do that in our case using R, right? Here, or were we doing it here? Yeah, we were doing it here only. Okay, so our data is what? As data means, right? So I'm saying plot as data means, not as data means straight away. I need to do the density, right? Density plot of this. Okay. So I get this curve. All right. And then what I do is I draw AB line in this. I say AB line, AB line. At what value? At a vertical point, which is mean of S data underscore means. All right. And I would prefer to change the color. So I say color is equal to, let's say, red. Okay. So I get a line here, which is indicative of where the data is kind of centered. So it's centered around here. All right. So this was my plot one. Okay. Now looking at the other parts. So this plot I've done. Okay. Now what I do is I also plot another curve. So I want to compare it with standard normal, right? So what I can do is this. If you notice, I say I use a function called curve. All right. And I want to plot the standard normal. So easier way is this. I say denorm. Okay, density curve, right? All of the values, let's say from -3 to 3. Okay, and then I say add is equal to true, which means the value, it should be added to the existing graph and not the new one. And then I say color is equal to, let's say, red. Okay, uh, let's see what happens. Wait. Sorry. How it works is this way. I say x. So basically curve plots any function, by the way. All right. And then I say the lower limit and the upper limit. So wait, let me explain the curve function to you first. So what has curve function done? It has plotted. What went wrong? Something went wrong with our values here. Oops. What I had done there was I had scaled the graph. Wait, hold on. So why did it go wrong? The 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 graph that I had earlier, I have actually converted it into a standard normal. Okay. So what I did is, let's say, what was my data? My data was S data means, right? So I say S data STD, standard normal, would be what? S data underscore means minus the mean of this data, right? I say mean of S data underscore means, all right? Divided by, I divided by what? Standard deviation of this data, right? I say standard deviation of S data underscore means, all right? Is this fine? Can I do this? When I do this and then I do a plot of so I do a plot not of the means but of the standard deviation, sorry, standardized data. All right, I do this. Okay, and then I also do an AB line on this. Let me make the color blue. Okay, let's look at what we've got so far. So this is what we get. All right, now the values are centered around 0, minus 2 to 2. Okay, so in the first part I wanted to show it as it is. In the second part I'll center it around 0, and then I compare it with, so I add another one which is a curve function, and so the red one is the normal distribution and the black one is the, so you can say they're approximately standard normal, right? So the data is actually approximately normal. Now what is the curve function? Say, let's say I said curve, all right, let's say sine. Okay, I want to plot sine from minus 10 to 10. Okay, sine of x. All right, I don't give anything else. Let's see what we get. Correct? So basically this is my x-axis and then sine of x comes here. So in our case what we wanted to do was I wanted to plot d norm. So density curve, right? It's a probability density function that is there, the bell curve that you see. So that is represented by d norm. Is this fine? Have you understood what I have done here to do the comparison? How many of you are clear? How many of you are not clear? Understood this? Right? So I compare it. So this is one way. The other way is using the Q plot. Okay. So how is QQ plot generated? Same. Basically, we state away that there's a function called QQ norm. All right. I say QQ normal. All right. What is my data? Uh, my data is S data uh, underscore STD. All right. Because I have to standardize this data. I hope I've done that. What I've done is here, easier way to do is scaling it also. See, I did that calculation, right? Data minus the mean divided by the standard deviation. If I just say scale the data, it will do the same thing basically. Okay, so there's a function called scale. So, in fact, I don't even need to do the standardized data. Let me just do for means data. I say means, okay, and let's say color is equal to blue. Okay, let's see what we get. So something seems to have not worked out well here. Yeah, it took some time. Theoretical quantiles. Yeah. Do you see what is happening? We're getting the data which goes this way. So your quantiles are how, so it will automatically actually create a standard normal. We don't need to bother. Oh, you can't hear me? Hmm. Hmm. How do we go about it? Abhishek, you can hear me? Any of you can hear me? So who all? Abhishek? Okay. Debushri? Nandana? Okay. So did you get what we did here? So we get a line which is like this. We saw in the previous case, right? Remember that in our case the sample, the degrees of freedom are how many? 39, right? Because the sample size is 40. So therefore degrees of freedom 39, we get a decent enough curve, right? And then we compare it against the normal. What we do is we draw another line which is QQ line, right? So we can straight away just do a QQ line. So basically it will draw a quantile uh, line. Okay, so if I was to execute this line of code, I say QQ line. s data underscore means. All right, say color is equal to red. Okay, so now what I get here is, oops, you can't hear me. Devashri cannot hear. Sarvani, you can hear. Abhishek, you can hear still, or something has gone wrong with the signal? Are you guys able? Abhishek can hear me. Okay. Devashri still cannot hear me. Okay. Devashri apparently cannot hear. So there is this problem with the signal at your end today. Okay, let me just move ahead then. So because I wanted to compare it, right? So what I do is I draw another line, which is QQ line, all right? And that line is nothing but uh, it actually gives uh, the actual theoretical quantiles that should be there for this data. Okay, or basically it just draws a line between the two. So we see that the two are quite comparable, right? Then so basically this is what is Q plot. So if the two lines are comparable, or the two, so there's this and there's this. Now, but this is too thick. So what I'll do is I'll change it. I say QQ norm. Okay, perfect. So I say PCH is equal to 20. Now PCH equal to 20 makes it small. Okay, I'll show you the. So I'm redrawing this. Okay, and then I do again redraw the Q line. So this is what my graph looks like. Oops, hasn't changed actually much. Anyways, all right. So this is it. So then I write a conclusion that the density plot and the QQ plot comparison suggests that the average data is approximately normally distributed. And I said further tests like Shapiro. So there are more tests which have not been taught in the class. So that these tests will be required to be performed to test whether the distribution is actually normal or not. Okay. So this takes care of the first part of the assignment. What I recommend is this. You go on Google, all right. Let me do a new file. Okay, new window. Okay, so what you do here is you got to type statistical inference. So what has happened is in this month onwards, these guys are saying you have to submit PDFs. The previous months, this assignment was to be submitted on RPubs. Okay, so what happened is people who have submitted on RPubs, that part is visible for us or for anyone else. Okay, so you can see the assignment submitted by people in the previous months. The questions were slightly different, but at least it'll give you more variety about the same answers, right? So I'm saying statistical inference, and I'm saying, so I'm searching it in which website? I say www.rpubs.com. By the way, this is the way to search in a particular website, by the way. Huh? I don't know if you know this command or not. Were you aware of this command? How many of you are aware of this command? So if I do this, so I get different people have submitted this project. I'm going to open these. So this guy has done it. So I say open it in a new tab. And then somebody else has done it. I say open. Somebody else has done it. I say open. Okay. So this is project part 2. Okay, so I get some more. All right. Okay, so let's look at them. So here is something done by somebody. Okay, and you can see his outputs, right? What he's done. So remember, another thing is we use the set.seed so that you can repeat your experiment. All right, something similar he's also done. Okay, so but he's plotting the histogram. I prefer to plot, yeah, I prefer to plot the density curve, right? So density curve is a better uh, fit. So in the previous assignments there were 4 questions. Now we have only 3. So similarly, here is something else. I think this guy has, yeah, he's just showing that the mean actually looks like this, but if you plot a density curve of the same mean, it looks like something like this. So he's doing all these calculations. So coverage is not required as a part of our assignment. Okay. So is this fine? How you can look for others projects? Don't copy paste from them, just for understanding. Understanding becomes much faster and better when you look at what others have done. Okay. So he's done the same thing here using different pieces of code. So you have enough samples also, right? To compare it with. You know how to search. Good enough? Shall I move on to the second part of the project? We're done with the first part. Can we move on to the second part? All right. So is this enough? No, I don't need to send the links myself, right? You can manage this, no? You know how to search it for now. Okay. So second part, let's all. So similarly, I've searched so this project is called tooth growth. So this is how I searched it. I said tooth growth www.rpops.com. Okay. So whatever I got, I started opening it up. So we will look at what the question says, and then so my question in Coursera says, so even I have to complete this, by the way, huh? I have not yet done it. So he says load the tooth growth data, it's an inbuilt data, okay, and perform some basic exploratory data analysis, then provide a basic summary of the data, use confidence intervals and or hypothesis test to compare tooth growth by sup and dose. What does that mean? We'll look at it. First, let us look at the tooth growth data. So what we have here is, first thing I need to load the data, right? So this is my part 2. So I need some libraries. I mean, that's how I have written my code. Therefore, I need them. In case you need them, you can write the libraries. Okay. So first is I say data. I say data tooth growth. Okay. Then what I do is so let us look at head of, just to make things simpler, right? I say TG is equal to tooth growth. Okay. So I say head of tooth growth. So this is the data. Let me just do str of tooth growth. So it has only 60 data points and 3 variables. What are the variables? Length, SUPP and dose. Okay. What I do is, let's say I say unique of, I want to see how many unique values are there for. Now SUPP is a factor, right? So I say how many unique values are there for TG dollar SUPP. So basically it's a supplement. So what is this data? You can see help. You can say help of tooth data. So tooth growth. So if you go to the help, it says a effect of vitamin C on tooth growth in guinea pigs. Okay. So the response in the length. So how long has so basically guinea pigs have been given vitamin C. All right. And then they want to see how much the tooth has grown. Right. So we've studied, right? Or in childhood also you should eat things which have vitamin C, your teeth, or calcium and everything, your teeth will be better. Right. So pigs at each level of so guinea pigs at each 3 levels. So they are given. We'll look at this data first. Let us see what he's saying. So 2 things. One is absorbic acid, another is organic orange juice, right? So orange juice is represented by OJ, and absorbic acid is represented by VC. All right. So so your VC represents absorbic acid, all right. Okay, so we have these three data points. So dose is in milligrams, okay, and how much, and data frame with six, we've seen this. So two delivery methods are there, dosage levels are there, and the response is the length, how much the length has increased. Is the data clear to you now? Huh? So if I was to, so this is how the data would look like. Okay, so I want to do some more exploration of this data now. So what I do is, what I can do is I can create a summary of this data. Before that, yeah, so I create a summary. I group it by dose and supplement, right? So I've seen that the unique for supplement is this. Let's see what about the dosage. I have no idea how the dosage is going to be, right? So I say dosage of TG dollar dose. So I get three values, 0.5, 1 and 2. But know that they are not, it's not a factor, it's a number. All right. So I have three dosages and two, three dosage sizes and two supplements. Okay, two medicines. So now, if I was to do the whole of TG data, I get 60 data points, but I can't make out how many records are there where one. So what I do is I will do this. I would kind of summarize my data. All right. I say, so I use dplyr. Okay. So I have always preferred to use dplyr. So I use dplyr and then I say TGS is my summary. All right. So I use TG is my data. So this is the syntax. Okay. TG percent dot percent. So there could be this problem with percent dot percent in Windows machines. I think it has to be something else. Okay. So I group my data by dose and then supplements. Okay. And then I say I want to summarize it by, first thing I want to do is just the records. Okay, how many records are there? How many rows are there? So I say records is equal to n. So function is n, right? And then let me print tgs. So what do I get? Apparently there are 10, 1, 2, 3, 4, 6 combinations. For these 6 combinations, for each of the combinations, 10 records are there. So looks to me like, so what they had is, though they had 60 records, they are saying that we have the sample size of 10 for each of this combination, dosage and supplement. Is this fine? So, but is it the same guinea pigs or different guinea pigs? How would you know that? So though the data shows 60 records, is it the same guinea pigs or different guinea pigs? Because these are the kind of questions that you would need to ask when you come across the data. How can you figure that out? Is the question clear? So how will you figure out whether it is the same guinea pigs or different guinea pigs? Or is it just 10 guinea pigs? Rather, is it 10 guinea pigs who have been, done with this experiment again and again? Or is it 60 guinea pigs? Is the question clear? All right. So what is your answer? Okay, we'll check with 60, but the graph won't tell us anything. What we can do is, on what basis are you saying 60, Abhishek? Your answer is correct, but what is the logic? So what I'm doing is I'm once again looking at the help of tooth growth. Does it tell me anything? Okay, that is why sometimes reading help is good. So the help says response is the length of teeth in each of the 10 guinea pigs at each of the 3 dose levels. When you use the word each, which means what? With each of the 2 delivery methods. Very clearly, it means that the There are 60 guinea pigs, so he's creating 6, right? So always read up information about data when you're performing your analysis, whenever in doubt. Okay, so all the information and help files. So in this case, it's an inbuilt data, right? When you get data from outside, a lot of times there will be help files associated with it which will explain that data. Okay, all right. So we've seen this. What I want to do is I can use my same set of code to get more information about the data. So I also want to check the mean. So I say, so the beauty about of the summarize function is that I can create many functions. I say records, then I say my mean length. Let's say, right? I say my mean length is equal to mean of what? Length, right? Whatever is length per group. Okay. Now if I do that, what do you see? I also see the mean for each of these combinations. So I see that dosage is 0.5, the mean is 13 for orange juice and 8 for absorbic acid. Similar, and it is higher for higher dosage, further higher for the higher dosage. I can also create my, so I can keep changing my function here, and I say standard deviation of length, okay, is equal to SD of length. Correct? So what I have done in my case, I've taken a couple of these inputs. Okay, so you don't need to exactly do how I have done, because no one else has shown this table I've seen. Okay, you may or may not, based on how you're understanding or how you want to do it. So from this above, we can say there are 10 records of each of the. Let me just knit it for you. So this is how my output looks like. Okay, what do I do first is I just do the tooth growth, and then I take a str of that. Okay, next thing I just create the summary. All right, next thing I'm going to plot it. Okay, now before I show you my stuff, let's just also have a look at what all different people have done. So this is what somebody else has done. Okay, and then someone else. Okay, so here's another solution. Okay, so this guy has plotted it this way. All right, analyzing tooth growth, and I've seen most of the people have actually plotted it this way. So they've plotted such that the dosage is there here, and the so it doesn't matter. There's nothing standard that you have to use. You have to just see how you want to analyze your data. Okay, so similarly, he's done some slightly different style of plotting it to understand. Okay, and so on. Is this fine? So please look at different people what they have done. One is, it will make it easier for you to write down what you want to write. Okay, because when you read so many people, then you know, okay, what you want to write. All right, and secondly, it'll be faster. So coming back to uh, our question first, what was it that we needed to do? So he says perform a basic summary and then perform some basic exploratory data analysis. So what I've done is I have used a ggplot command. Okay, so just to remind you, so ggplot, what you need to do is just mention the data first. Once I mention the data, then aesthetics, which means x-axis and y-axis. In my case, I've taken x-axis as supplement, SUPP, and y-axis as the length of the teeth. In all cases, anyways, y-axis is of interest because that is the response parameter, right? Because here, eventually what he's saying is use the confidence interval, etc., to compare tooth growth by supplement and dosage, right? So that's what I have to compare. So I said this, and then I said fill by supplement. What will that do? It will give colors based how the supplement changes. So for different supplements, the color will be different. Okay, and then I want to plot a box plot. So if you notice, somebody else had done lines, okay, or points. So I'm doing a box plot, or rather, and then I'm giving it a title, and then I create grids. So I want to do a separate one. So I say create grids by dosage. Let me just show you the same thing without the grids. Okay, and with the instead of geom underscore box plot, let's say points. Okay, so this is my code. I'm just executing this and let's see what we get. All right, geom underscore point. So this is what it looks like. What do I have here? I don't know if it is visible or not, but length here, factor is dosage, because this is what I said. By the way, I've taken factor of dose. Why? In the aesthetic part, the x-axis has to be a factor. Otherwise, what will happen is it will become linear. All right, and then it will become a problem. Let's do this. Let me knock off the word factor from here and see how it changes. In this case, it will not change much because the data is anyways for 0.5, 1 and 2. But otherwise, this can be a problem. Let me just select this line of code, execute it one more time. Right? Do you see what has happened? What is the bigger problem? 0.5, 1 and 2. So there's a gap because this will be considered as a linear line now. Have you understood why I used the word factor there? So this will kind of categorize it, so then that problem will not be there. Okay, so in my, I say, look, the points doesn't make sense. I say, let me draw a box plot. Okay, so I say box plot. Okay, so I do a box plot, and because I've said fill is equal to factor dose, I get the colors also. Now what I'm saying that, look, fine, this is great, but maybe I'm more interested in also seeing the split up by the supplement. So what I do is I add this to this itself. So just to show that actually this, I say, so I say plus facet grid, and then I take the, so I execute this. Sorry, I had anyways plotted those here, right? So my supplement should, facet should be maybe supplement, right? So that's how it will work. Got it? What I've done? And I could reverse this also. I could say this supplement here, okay, and fill factor also supplement, and facet grid dosage, which means now my data would look this way, right? So I've just kind of restructured it. Is this fine? So now when I look at any of these curves, either this or the other one, what can I conclude? Certain things can I conclude from this, or let's say this. What can you conclude from this, or what does this graph tell you? One thing that it tells you for sure is that if the dosage is low, the length increase is low. So there is some correlation between the length, or proportionality between the length of response of the tooth and the dosage amount. First thing. Secondly, if I just look at this, it seems to tell me that for dosage levels, this is like say 0.5 and 1. I see that at least in this, it says orange juice seems to be better than the absorbic acid for the increase in the length. Whereas when the dosage level is high, which is 2, both of them seem to be giving you the same result. All right. So only thing is that there's higher variance in this case. Okay. So this is what exploratory data analysis is telling us. Further ahead, to actually even test, and if we were to assume these as our hypothesis and actually test it, we will need to perform some t-tests, and we haven't learned that yet. Okay. So how do we want to go about it? I want to just so in fact, even I have also done fill so far. Okay, I need to cover up the other two parts of the project. So either maybe some session tomorrow evening or tomorrow night after my session gets over. I have a course, Sunday's full day. Okay, I could spend some part on this, or maybe you can look at all of these examples all right, and they have the code here. You will be able to understand it. Plus, you refer to the only the first part is good enough. Hopefully, the week 3 class I haven't touched that, by the way. So we are running behind schedule. Okay, so I project is something which does not have a, it has a hard deadline, right? Quiz we can still postpone and take it. So project, maybe you understand things from here and you sort it out, or however you want it, we can do it that way. Either I can kind of take a class tomorrow evening to finish off this. How do you want it? You suggest. So actually it's a very simple thing. It's just a one line of code, that is t dot test. All right. So t dot test is actually going to test these things out. Uh, uh, and there's something called pair t test. So that was our topic of interest today, which we didn't. Let me see. By the way, how do you create the PDF? You know, the easier way is that you create the HTML and then save that file as PDF. Okay. So the students t-test, all right. If you go through the Wikipedia, would explain it to you basically, and it does it better than anything else. Plus, you can uh, go through the swirl part, right? So swirl is also kind of explaining it. It is making you go through certain things, and you will understand that. So shall we kind of leave it at this? So swirl you go through, and you go through search for go through the wiki for t-test, all right, and of course go through what other people have done. So just to repeat this, let me just do it here. I say tooth growth, all right, and website is rpubs. Okay, so I have a lot of these opening up, so I can open each of these and look at them, right? So I already have that here. Is this fine? Okay then. You may or may not be in a position to take the quiz number quiz number 3, but certainly for sure the project part you can kind of manage. Okay. Uh, uh, I don't know if so Abhishek, you have enrolled for this course this month, or you're going through the lectures and then you will be enrolling it next month. How is it? Sarvani, I'm sure you would have enrolled. Debashri? Next month. No, good. So you have time. So basically what you can do is kind of understand things. All right. And okay, so Debashri and Sarvani have enrolled. So maybe I can spend time with you guys if you need it tomorrow night. How do you want to do it, Sarvani, Debashri? Today we'll do the work, right? So tomorrow, if there is a need, then I'll be available. That way we'll do it. I'll take care of it. Okay, yeah, sure. Done. I think we'll close the class for today.